Welcome to qnawire.
This is problem 16 of chapter 23. In this problem, we are given two wavelengths. Well, actually, we're given one wavelength, 630 nanometers, and we are giving two distances from the 0th bright fringe to the first order bright fringe for those two wavelengths. So let's go ahead and write all of this down. We are giving one wavelength. Let's call it lambda A. This one is 630 nanometers, which is 630. We'll just leave it we'll leave it in nanometers because we're going to be doing a proportional argument. We're also given the distance from the 0th order bright fringe to the first order bright fringe. So let's call that y1, but since this is with respect to this wavelength, I'm also going to put an a there. So that distance is 0.51 meters. The distance to the first bright fringe of the second wavelength is also given, so we're going to denote that with a little subscript b there. It's given as 0.43 meters. And we are asked to solve, given this information, let's solve for the wavelength of this second light that's going through the grating. So for the grating here, we can assume small angle approximations because the slits in the grating are on the order of thousands of lines per centimeter. So here we can make the small angle approximations that sine of theta is approximately tangent of theta. So for sine of theta, recall the formula d sine of theta m is going to be equal to m lambda. And then here we can solve for sine of theta m. And also recall that tangent of theta m is going to be equal to ym over L. So we can set these two equal to each other in the small angle approximation case, which we're going to assume for this diffraction grating example. We aren't given L here, and we aren't given D here. So that's why we're making this approximation, so that we can set these two quantities equal to one another. And we're also not given the angles. Okay, so here we're going to set both of these equal to one another. We're going to have m lambda d equal to y sub m over L. So here we can go ahead and solve for the y sub m's because that's what we're given for each of these wavelengths. Okay, so this is an expression for ym. So what we're going to do is we're going to express these values in terms of this equation, and then we're going to divide the equations by one another. Okay, so let's go ahead and express that first distance, y1a. Okay, according to this expression here, m is going to be equal to 1 because it's the first ordered bright fringe. Lambda is 630 nanometers. L is not given, and neither is D. Okay, let's go ahead and express the other one. Y1b. This is the same order bright fringe, so it's going to be 1. We don't know what the wavelength is, so this is lambda b. We also don't know L, and we also don't know D. So what we're going to do now is we're going to divide one equation by the other. So let's go ahead and set this ratio. It's going to be y1a over y1b. So on top we're going to have this expression, And at the bottom, we're going to have this expression. Let's go ahead and put a bracket around that. Notice that L cancels out and so does D. So whenever you divide by a fraction, it's the same thing as it's multiplying by the reciprocal of it. So let's go ahead and do that, and let's get rid of the ones because that's not going to change anything. So we have 630 nanometers times L over D, and again we're going to multiply by the reciprocal of this denominator. This is going to be D over lambda sub B times L. Notice that the L's cancel out and so do the D's. So what we're left with here is 630 nanometers over lambda B. Okay, we are solving for lambda B. So let me rewrite this expression. We are solving for lambda B. So a quick way to do this is just to take the reciprocal on both sides. Let's go ahead and do that. And I'll multiply 630 nanometers on both sides, and that will give us the answer. Let's make some space here. So again, multiply both sides by 630 nanometers. So we're going to get lambda B. It's going to be equal to 630 nanometers times that ratio y1b over y1a. Now we plug in all the values. Y1b is 0.43 meters and y1a is 0.51 meters. Meters cancel out with meters, leaving nanometers. So our lambda b is in nanometers, and this comes out to be 530 nanometers for our final answer. This concludes problem 16.